So my blue is my placement function, my cubic right here. Notice that now that I've changed to a cubic function, that my derivative is no longer a line. My derivative now looks a whole lot like a quadratic. And I will tell you that the derivative of a cubic will always be a quadratic. So let's try and figure out what that equation of the quadratic is. We see that it goes through the origin. And so what I'm going to do here, because we don't really have like a slope-intercept form kind of situation, we can use our vertex form. So y equals a times x minus h squared plus k. Remember that h and k are your vertex, and we know, I can tell you, that the vertex, it looks like it goes through the origin. If we trace it, 0, enter, we see that it does go through the origin, and that is our vertex. So if hk, our vertex, is 0, 0, hopefully this is bringing back some memories about finding equations of quadratics. If not, I would recommend looking back at your notes from last year because we did learn this. So I will plug this back in for h and for k. Y equals a times x minus 0 is still x squared plus 0. So really, we're at ax squared at this moment. And what I need is just any point that's on that quadratic in my graphing calculator to plug in for y and for x in order to solve for a. So going back in and grabbing that, if I hit trace, maybe I'll do 1, enter. And 1's a nice point. It's 1, 3. So I'll go ahead and plug that in. 1 goes in for x, 3 goes in for y, so 3 equals a times 1, hey, a equals 3. So the equation of our derivative function for this guy right now is y equals 3x squared, right? We plugged in 0, 0 into the vertex form, which got rid of this hk situation, and then we got to here and said, hey, we still need to find a. We plugged in an example point, which got us to figure out what a was, and now we have our complete derivative function. Compare it for a second back to your original function and try and compare it to what your hypothesis was about what is going on here between the relationship of a derivative and its placement function. Okay, we're going to do one more. Again, I'm going to go back to my F1, delete that guy, do 1 divided by 2 times x cubed. Again, cubic here, you can see that we've changed our cubic function. Our quadratic derivative function also changed, still going through the origin, which is really nice. So I do know that I'm going to have this situation again. So I can just kind of automatically jump to that. Y equals ax squared. And my thought is, what does a equal, right? What does a equal in order to know what the equation of this is? I would like for you to go ahead and tell me and find what does a equal. Remember that before, when we tried to find out what a was, we grabbed an example point from the quadratic. So go ahead and try and figure it out. Okay, I hit trace. Whoops. There we go. 1.5, okay, kind of nice. I could go 2 maybe to get a whole point. I like that just a little bit more. So I'm going to go ahead and do 2, 6 in order to solve for a. It doesn't matter which point you found. You'll get the same value for a. Plugging in 6 for y equals a times 2 squared. So 6 equals 4a. Dividing both sides by 4, I get 6 over 4, which simplifies down to 3 over 2. Which, hey, is 1.5. Remember that we started with 1.5. But I do think it's nicer to see this one when comparing your final derivative function to the original. So again, pause and look at all of these situations, the derivative back to its original, and try and think about what is the relationship there. So finding your derivative in an algebraic way means that you are using for a polynomial function, which is the only type of one that we're going to learn how to find the derivative for. There are lots of other ways, but we will only learn the power rule. So the power rule is for a polynomial function, and it could be a polynomial for a function of the form f of x equals a x to the n power. So a is your coefficient. A is your coefficient, and n is your exponent, and it could be anything, right? It could be to the third power, to the second power, to the first power, to the zero power, to the negative power. It can be a lot of different things, and a is just, it can be an infinite number of things, and a is just your coefficient. So then we're just saying, hey, and this is a polynomial of any type. The derivative takes the form f prime of x, right? Prime meaning derivative, equals a times n. So think about that. We take the exponent and we multiply it to the coefficient, right? 2 times 1, 2 times 3, 3 times 1, 3 times a half. So we take our coefficient and our exponent and we multiply them together, and then we still have x there. But now what happens to the exponent is we have one less of it, n minus 1. So when we started off with a squared or a quadratic, we got to a linear or to the first power, right? Squared goes to a first power. Cubic goes to a squared power, always. Oh, I wrote a squared. You probably at home caught that. I did not. A quartic or to the fourth power will always have a derivative function that's a cubic. A quintic or a fifth power will always have a derivative that's a quartic. It always just goes down by power. And that's it, the power rule. That's how you find it algebraically. So let's process it. Let's practice it and process it. Okay, so if we were to practice it, what we need to do is we know that, okay, we're talking about the derivative here. We take our exponent and we multiply it to the coefficient. The coefficient here is 1. So it's 4 times 1. And then x to the, and then we do 1 less, 4 minus 1 in the exponent, which means it's 4x cubed. That's it. It gets maybe a little bit harder, but not that much. I think the hardest part about derivatives in this unit is just knowing when to use the derivative versus the original function and how they relate and what they bring in, which is the hard part, and you've already done that. So now you're just learning how to find it algebraically, which is arguably the easiest part. Okay, so practicing it again. What we need to do is we need to take our exponent and we need to multiply our coefficient by the exponent. So our derivative is equal to 10 times 2 times x to the 2 minus 1. Okay, so that's 20x to now the first power. Y equals 15. So y equals 15 is a constant. 15 is a constant. It's not a polynomial. And what happens to our constants, just a number with no x or anything on it, is it just goes away. That its slope is 0, and so finding the derivative of that is just that there is nothing. So the derivative of y equals 15 is 0. Because the slope would just be 0.